Welcome to Math with Professor V. This is video lecture for section 3.2 for business calculus on continuity. Now, up until this point, you may have heard other definitions for continuity, but now we're going to define it in terms of limits. And there's a three-part definition that we're going to refer to as calculus students. So here we go, continuity at x equals c. We say that a function f is continuous at x equals c if the following three conditions are satisfied. First condition, f of c is defined. So the function is defined at that value, x equals c. Second condition, the limit as x approaches c of f of x exists. And third condition, the limit as x approaches c of f of x is equal to f of c. Sometimes when you'll see the definition of continuity, only this third condition is listed. What the third condition states is that the first two conditions are equal to one another. So obviously, in order for this to be satisfied, the first two must exist and be defined. So this sort of encapsulates all of what's going on. And keep in mind too, when we say that the limit exists, remember it needs to be a finite number. All right. Now, definitions that you may have heard before for a function being continuous at a certain point would involve saying something like you could trace the graph of the function without having to lift your pencil or stylus at that point, but that's a more informal definition. So we're going to be referring to this three-part definition to answer the following questions. And if for some reason a function fails one of the conditions for being continuous at c, then we say it is discontinuous there. That's the same thing as not continuous. Alrighty, so let's look at some examples here. Determine if each function is continuous at the indicated x value. So first one, we're looking at x equals 3. So let's go through the three-part definition. First, I'm going to check, is f of 3 defined? And bam, right off the bat, you can see, no, it's not defined. There's a big old hole in the graph. So we have no function value. We have no y value at x equals 3. So that's all you need to do. If it fails one of the conditions, you don't need to go through and check in order to verify continuity, unless you're asked to, check all three conditions. I could see, though, that the limit does exist if we wanted to get into it, because the limit from the left of 3 is equal to the limit from the right of 3. So the limit does exist. The problem here is that the function is not defined at that point. So then we can just say this means the graph or the function f of x is discontinuous at x equals 3. Okay, very good. Let's look at another example now. Here we have h of x, and we're investigating what's going on at x equals 0. So first thing I'm going to check in my three-part definition is h of 0 defined. Is the function defined when x equals 0? So notice here there's an open circle, but at this point where x is 0, we have a closed circle. So the function is defined at x equals 0. Let me zoom in so maybe you can see a little bit better. So is h of 0 defined? Yes. In fact, we can say h of 0 is equal to -1. All right, well then let's check the next condition. What I want to know is, does the limit as x approaches 0 of h of x, does it exist? And in this case, I need to check the limit from the left of 0 as well as the limit from the right of 0. Because remember, when we don't indicate from which side, this is a two-sided limit. And in order for it to exist, the limit from the left has to be the same as the limit from the right. So let's check. So let's see, what's the limit as x approaches 0 from the left of h of x? And what's the limit as x approaches 0 from the right of h of x? And you guys, I have to point out something crucial. Don't forget to write h of x, h of x. You can't just have nothing right there. So we always write lim, x approaches some value, and then you have the function, or you actually write the equation of the function. A lot of the times I see students just don't write this part, but that's incorrect, okay? I I don't want you making those mistakes too. Okay, so what's the limit as x approaches 0 from the left of h of x? So this means we're coming from values smaller than 0. So we're on this part of the graph. We're walking, 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 you can imagine. What y value are we approaching? Remember, the limit is the y value. We're approaching -1. Now, if we're coming from the right of 0, then we're over here on this part of the graph from values larger than 0, walking, 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 or running, you do what you want. Where are we going? What y value are we approaching? We're approaching +1. So notice the limit from the left does not equal the limit from the right. And that might have just been obvious by looking, but we're verifying using our definition and practicing nice function notation and limit notation. So from here we can say, all right, this means the limit as x approaches 0 of h of x does not exist, DNE. So condition 2 is not satisfied, which means the graph or the function is discontinuous at x equals 0. All right, very good. Now let's look at one more example. We're investigating what's going on at x equals 4, and this time our function is called g of x. So let's go through our three-part definition. First thing I want to check, is g of 4 defined? Well, let's see. If I substitute in 4 for x, what is the y value or the function value? There's a hole here, but have no fear. Someone came and gave us a one lonely little point here at x equals 4, and it corresponds with y equaling 1. So then we could say, yes, g of 4 is defined. It's equal to 1, thanks to this lonely little point right here. Okay, next thing we're going to check, does the limit as x approaches 4 of g of x exist? So let's check our two-sided limit. In order to verify that the two-sided limit exists, we have to check from each side, So we want to see what's the limit as x approaches 4 from the left of g of x, and then what's the limit as x approaches 4 from the right of g of x. Let's see. So from the left of 4, we're coming from values that are smaller than 4, and we're always on the graph. So we're walking on the graph from values smaller than 4. We're approaching y equals -2. From the right side, you probably noticed we're going to the same exact place, y equals -2. So yes, we can say the limit as x approaches 4 of g of x equals -2. So far, both conditions 1 and 2 are satisfied. Things are looking up. Now, the third condition is that the result from conditions 1 and 2 are equal to each other. So does g of 4, does it equal the limit as x approaches 4 of g of x? Well, no, g of 4 is 1, and that's clearly not equal to -2. No, so the third condition failed. So we can say at x equals 4, the graph is not continuous or discontinuous. All right, now we could fix this discontinuity, right? Everything was going great up until this last moment because the function value is not equal to the limit. And we could fix it by just saying this point, why don't we just move it and fill it in where the hole is? Why is it floating up there all strangely? That's what ruined everything for us. And so that is an example of a removable discontinuity. Let's define it. When the function can be made continuous at a specific point simply by defining or redefining it at that point, the function is said to have a removable discontinuity. And if we want to get more technical, in order to have a removable discontinuity, the second condition of continuity must be satisfied. The limit has to exist. And if that condition is satisfied, then we can always define or redefine the function value in order to make the limit equal the function value for condition 3. Now, this isn't always possible. So if the limit does not exist, if condition 2 is not satisfied, then our discontinuity is non-removable because it can't be fixed by redefining the function. And I just want you to look back at the previous example that we graphed, or that we looked at its graph of h of x here. This one didn't satisfy condition 2. The limit didn't exist. And you can see we're not able to fix the discontinuity or remove it by simply filling in or redefining a point somewhere. It's because the limit from the right and left are not equal at x equals 0. So this is not removable. This one is removable. We would just need to fill in this point here. Okay. Now, it is tedious, as you can see, to check these conditions 1, 2, 3. And thankfully, we have a theorem that allows us to just identify what kind of function we're dealing with, identify its domain, and from there we can already know where it's continuous and not continuous. So this is very important. Make sure you put this to memory right here. So polynomials, rational functions, root functions, exponential functions, and logarithmic functions are all continuous on their domains. So what that means is if you have a function that falls into any of these categories, then all you need to do is identify its domain. Whatever values are not in its domain are where that function is discontinuous. And we can always add to this list and include trigonometric functions, inverse trig functions, but we don't deal with those in business calculus. So we're not going to talk about that. But basically you're saying, you might look at this list and go, man, oh man, everybody seems to fall into this category of being a continuous function, pretty much. The only ones that don't apply here would be piecewise defined functions. So we're going to have to investigate those more carefully. So not piecewise defined functions. But besides that, pretty much everybody, we can just say it's continuous on its domain and then identify the domain. So let's practice doing just that. So for the next few examples, we're not going to check conditions 1, 2, 3. We're going to use this theorem here on continuous functions. It's not listed as a theorem in this text, but other calculus texts do list it as a theorem. So find all values x equals a where the function is discontinuous, not continuous. For each value of x, give the limit of the function as x approaches a. Be sure to note when the limit doesn't exist. And in order to help us out with some of these limits, I've included the graphs of the functions, and they're all generated from Desmos if you want to go verify for yourself. Okay, so f of x, first before I go ahead and apply this rule here, let's identify what kind of function f of x is so that I know I can go ahead and say, oh, I'm just going to look at its domain. So f of x is a rational function, yes? When you have a ratio of polynomials, basically polynomial in the top, polynomial in the bottom. So f is a rational function. And all we need to do now is identify its domain. So when we have a rational function, remember, we don't want the denominator to equal 0. So the restrictions are going to come from setting each of the factors of the denominator equal to 0. So what we don't want is for 2x plus 1 to equal 0 or 3x plus 6 to equal 0. So I don't want x to equal negative 1/2, and I don't want x to equal negative 2. So if I list the domain for this function, remember, you write all x's such that x cannot equal negative 1/2 or negative 2. So these are the values where the function is discontinuous. Discontinuous at, I'll just rewrite it, x equals negative 1/2 and negative 2. Okay, so when you say where a function is discontinuous, you put an equal sign. When we're writing the domain, we put not equal to because those values cannot be substituted in for x into the function. Okay, now one more thing we need to do. It says, for each value of x, give the limit of the function as x approaches a. All right, so each of these are the a values. So I want to know what's the limit as x approaches negative 1/2 of f of x, and then what's the limit as x approaches negative 2 of f of x. And we're just going to use the graph, okay? So you can see here, this is where x equals negative 1/2. We have a vertical asymptote. And then this is to the left of it is where x equals negative 2. I think that you can see more clearly. And remember, we studied rational functions earlier. Wherever the denominator was 0, we had vertical asymptotes once we fully reduced our function. Okay, well, I'm looking here. Let's talk about negative 1/2. Let's zoom in. This is x equals negative 1/2. If we're approaching from the left, the function's going to negative infinity. If we're approaching from the right, the function's going to positive infinity. So therefore, what would we say the limit is as x approaches negative 1/2? It doesn't exist. So you erase that equal sign because it doesn't equal anything, and you just put d n e. If you want a little reason, I'll say because the limit as x approaches negative 1/2 from the left of f of x is negative infinity, and then the limit as x approaches negative 1/2 from the right of f of x is positive infinity. Okay, good. Now let's look at negative 2. So negative 2 is over here. Again, same thing. From the left of negative 2, we're approaching positive infinity. From the right of negative 2, negative infinity. So get rid of that equal sign. It doesn't equal anything. The limit simply does not exist. And then everywhere else, f of x is continuous. So I don't need to check conditions 1, 2, and 3. If someone said, hey, is the function continuous at x equals 0? I'd say, yep. And I don't need to confirm checking 1, 2, 3 from my definition. I can just say f is rational. It's continuous everywhere on its domain. Nice, right? Okay, next one let's look at is f of x equals e to the 1 over x. So let's see, what kind of function is this? It's a combo. It's a combo of an exponential and a rational function. But that's fine. We can make combinations of functions and still apply that rule from earlier. So where is f undefined? Or basically, let's identify its domain. Right away, I noticed this is 1 over x. So x can't be 0. So the domain is all x's such that x can't be 0. So that means the function f is discontinuous at x equals 0 or a equals 0, doesn't matter. Okay, I happen to have the graph for you right here. And this is e to the 1 over x. So let's identify the limit as x approaches 0 of f of x. And remember, in order to do that, first we need to look at what's the limit as x approaches 0 from the right of f of x, and then what's the limit as x approaches 0 from the left. So from the right, imagine you're walking on the graph, you can see it's going up to positive infinity. And then from the left, oh, no asymptote, you're approaching 0. Well, clearly they're still not equal to each other. So the limit as x approaches 0 of f of x does not exist. All right, now you could have also done this limit without looking at the graph, and let's just practice that a little bit. So another way to do it without the graph, you could take the limit, x approaches 0 from the left. I'll write the actual function in e to the 1 over x, and then let's practice x goes to 0 from the right, e to the 1 over x. And you do need to make use of this one fact, so I'll have you recall. We talked about infinite limits in a previous lesson. The limit as x goes to 0 from the right of 1 over x is positive infinity, and then the limit as x goes to 0 from the left of 1 over x is negative infinity. I'll link a video on infinite limits in the description if you're curious to know more about why, but you don't need to stress about that in this course, more for like a pure calculus course. But if you just keep in mind the basic idea that it doesn't have to just be a 1 either, it could just be any constant that's positive. If the denominator is going to 0, it's shrinking, shrinking, shrinking. when you divide by something tiny, this whole quantity is getting very, very large. And since we're approaching through positive values, then the sign of this quantity is positive. So that's why it's going to positive infinity. And then if x is going to the 0 from the left through negative values, then this is getting very, very large, but in the negative direction. So it approaches negative infinity. So basically what you can do is use this idea here. X is going to 0 from the left. I know the exponent is approaching negative infinity, right? And then if you remember the graph of e to the x, so you do need to remember that graph on your own. So e to the x's graph, let's just draw it over here. This is e to the x. Just a really crude graph, I know, but it'll get the job done for our purposes. So the exponent's going to negative infinity. Where's e to the x going as we go to negative infinity? It's going to 0. And then as x approaches 0 from the right, 1 over x we know is going to positive infinity. Well, where does e to the x go? As we approach positive infinity, it also goes to positive infinity. So notice I got the same result without having looked at the actual graph of e to the 1 over x. I did need to know the graph of e to the x though. So this one's very important. Put it to memory because it's useful when computing limits if you're not given a graph. Okay? Good. Last example here. We have f of x equals natural log of x plus 2 over x minus 3. Ooh, okay, here's the graph off to the side. This is a spicy one to graph. Let's think about natural logs. When we first studied them, we noted the fact that the argument, this is always called the argument, whatever you're taking natural log of, this stuff. The argument had to be greater than 0. Well, we have absolute value bars, so I'm not worried about it being negative. The only thing that's making me nervous now is if it were to equal 0 or if I were to have a 0 in the denominator. So basically I have two restrictions. X can't equal negative 2 or positive 3. So if I were to write the domain for this function, I'd say all x's such that x can't equal negative 2 or positive 3. So that's exactly where f is discontinuous. Discontinuous at x equals negative 2 and 3. And then let's see if we can identify what the limit of the function is as x approaches those values. So what's the limit as x approaches negative 2 of f of x? And then what's the limit as x approaches 3? And just feel free to use the graph that I have right here. As x approaches negative 2, from both sides we can see the function's approaching negative infinity. And then as x approaches positive 3, the limit's going to be positive infinity. Very good. Okay. So now we've practiced using that theorem, that rule that tells us we can identify discontinuities of many functions just based on looking at their domains. And I said one kind of function doesn't apply, piecewise defined functions. So now we're going to look at some piecewise functions and investigate them. So here's what our task is. Graph the given function and then find all values of x where the function is discontinuous. And then lastly, find the limit from the left and from the right at any values found in part B where it's discontinuous. So if you look at this piecewise function, 0 and 5 are just constants and this is a polynomial. So I know within each of these little intervals, the function will be continuous. The tricky thing about piecewise functions is where different functions are being pasted together. So wherever the domain splits or changes. So we have potential issues at x equals 0 and at x equals 5. But I'm not worried about any other x values. Those are the only areas of concern. Okay, so the first thing we need to do is graph. So f of x equals 0 if x is less than 0. That's just y equals 0. Since it's not equal to, it's not an inclusive inequality, I'm going to have an open circle right here. And less than 0 means smaller to the left and put an arrow there. This I know is a parabola. Let's figure out what the vertex is so we can graph it nicely. Let me make this a little smaller since I zoomed in so much. Can I make it a wee bit tinier? Perfect. Okay, so y equals x squared minus 5x. Let's find the x coordinate of the vertex. So h is, remember, negative b over 2a. So negative 5 is positive 5 over 2 times 1. This is 2.5. And then the y coordinate of the vertex k is f of that x value, f of h. So that's going to be 2.5 squared minus 5 times 2.5, which is negative 6.25. So we can say the vertex is at 2.5 comma negative 6.25. So let's fill that in. So 2.5 and then negative 1, 2, 3, 4, 5, 6, and a wee bit more. There's 2.5. There's the vertex. Let me add some scaling too. 1, 2, 3, 4, 5. Ooh, that's too chunky. 1, 2, 3, 4, 5. Good. Here's x. Here's y. 1, 2, 3, 4, 5. Okay. Very good. And then I can just plug in the endpoints. See how it's inclusive, the inequality? So if x is 0, we get, very good, y is 0. So that means you're just going to come over here and fill in this closed circle. And then if x is 5, 5 squared minus 5 times 5 is also 0. So we have 2 zeros right here. We alternatively could have found the x-intercepts. Okay. You know, guys, hold on. That's ugly. Too ugly. Okay, that's better. And then lastly, the function is equal to 5 if x is greater than 5. Notice it's not inclusive. So I'll have an open circle at y equals 5. And then you're just going to shade to the right. Or draw a line to the right, not shade. Good? Okay. So where is the function discontinuous? You could use your 3-part definition, or you can just observe, right? The only 2 places that I said we were worried about were at x equals 0 and x equals 5. At x equals 0, we have no problems. The function is defined. The limit from the left equals the limit from the right. So x equals 0 is fine. At x equals 5, the function is defined, but the limit from the left does not equal the limit from the right. So that's where we have an issue. So let's go ahead and answer the question. We'll say it's discontinuous at x equals 5. And then they want us to find the limit and from the left and the right at that value. So the limit as x approaches 5 from the left of f of x, what does it equal? So from the left of 5, we're coming from values smaller than 5. So we're walking on this little piece of the graph. Hey, here we are. What y value are we approaching? Very good. We're going to 0. And then what's the limit as x approaches 5 from the right of f of x? So now you're walking on this part of the graph. What y value are you approaching? You're approaching 5. Good. So that's why you could see the limit as x approaches 5. The two-sided limit of f of x does not exist. Okay, good. Is this discontinuity removable? No, because the limit doesn't exist. So since condition 2 was not satisfied, the limit doesn't exist. It's not as simple as simply redefining or defining a point differently. Okay, very good. Last idea, find the value of the constant k that makes the function continuous. So remember, our issue here with piecewise defined functions is that the limit from the left may not equal the limit from the right, and we want the function value to equal that limit. So basically, what we require in order to force this function to be continuous is we need the limit as x approaches. What value of x am I nervous about with this piecewise function? I'm only nervous about x equals 3. So I need the limit as x approaches 3 from the left of f of x to equal the limit as x approaches 3 from the right of f of x. I'll repeat that. So notice here, this is just x cubed plus k, that's a polynomial. This is a polynomial too, it's a line. And I know they're going to be continuous on their domains, which are all real numbers. The only place that I'm nervous about is what's going on at x equals 3, because I don't know if these were pasted in such a way that the limit's going to be the same from both sides. So I'm going to force it to happen. I need the limit as x approaches 3 from the left of f of x to equal the limit as x approaches 3 from the right of f of x. So now let's see what it would take for that to be true. So the limit as x approaches 3 from the left, how is f of x defined from the left of 3? From the left of 3 means values that are smaller than 3. So it's equal to x cubed plus k. And then I need that to equal the limit as x approaches 3 from the right of f of x. How is f defined from the right? That's values larger than 3, and it's equal to kx minus 5. Good? Now, how would you evaluate each of these limits? I mean, there's no reason we couldn't just use direct substitution. X is approaching 3. Now it doesn't matter if it's from the left or from the right. That just helped me pick the correct equation. I'm just going to simply substitute in 3 for x into the respective functions. So we'll have 3 cubed plus k equals k times 3. Let's write 3k minus 5. Good? All I did was substitute in 3 for x. Again, I'm going to say the left and the right just helped us pick which function goes where, but then you just simply plug in 3 for x into both. Okay, then this means 27 plus k equals 3k minus 5. Let me add 5 to both sides, so 32 plus k is 3k. That means 32 is 2k, so k is 32 divided by 2, which is 16. And that's it. So as long as k is equal to 16, this piecewise function will be continuous. If k equals anything else, then it won't be continuous. Womp womp. So that concludes the lesson. I hope you enjoyed it. And continuity is a topic that's difficult for a lot of students, so just make sure you put to memory the 3-part definition as well as our rule, which is also a theorem in some text that tells us that polynomials, exponential functions, logarithmic functions, rational functions, root functions are continuous on their domains. That's super helpful. Subscribe if you haven't already. Don't forget to give the video a thumbs up, and I'll be back with more business calculus video lectures very soon. Also, if you're interested in reviewing or delving deeper into any of these topics, then check out the rest of my videos that are organized into playlists on my YouTube channel. And please follow me on Instagram, TikTok, Twitter, whatever. It's called X now. I can't make that shift in my mind. Math with